So we've been talking about the forms of energy, and we're going to get into each one of these a little bit more in depth and more detail. So we started with sound energy the other day, right? And some of the things we learned when it came to sound energy was that you had to have a solid liquid or a gas for sound to travel through, right? That's why you can't hear sound in space. If there is nothing for it to travel through, there is no sound waves. And we saw that video with the bell or the bell that was inside the vacuum. They sucked all the air out and you couldn't hear it. As soon as they put the air back in and the sound could travel through the airway or the air molecules, you could hear it again. We then got into the vibrations of of sound, because it travels in vibrations, right? Vibrating waves. And we said that the faster that vibration, the higher the pitch. When we did the lab the other day and we had the little box and I had the rubber band and I made it stretched really, really tight and I would pluck it, it was going real fast, right? And the faster it was going, it was that high pitch plucking ding, 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 ding kind of sound. When I made it longer and it wasn't as tight and I would pluck it, you would see it go whoa, whoa, whoa. And you could actually see the wave go slower. And the slower it was, you would hear it going boom, boom, boom. And that's why we have the different size instruments. Usually, the bigger the instrument, the more that sound waves has to travel through, the deeper the sound, okay? The smaller the instrument, the higher the pitch. Think of it like this. You guys have heard the piccolo, right? You guys know what a piccolo is? A mini flute? No, that doesn't work, okay? How about a clarinet? You guys know what a clarinet is? Versus a big tuba. Which one has the deeper sound? Tuba. Why? Because it has so much more that the sound can travel through, so that the sound waves are traveling so much slower. Slower, lower, faster, higher, okay? We are now going to move into thermal energy or heat energy. And there's a couple things that you need to know about heat. Okay, thermal energy. What is thermal energy? Thermal energy is the movement of atoms, right? And they're rubbing together. So we talked a little bit about this the other day, right? That's not working very good. I can't see it. Oh, let's see. Let's do that. See if that helps. Not at all. Let me move out of the way. It's still not helping. Let me try something. Hold on. Let's see if that works.
Yes.
Not at all.
No. Oh. I see it.
Okay. Unlike people, it'll come up here in a little bit. You'll have time to copy these notes. But the faster the atoms are rubbing together, the more heat's produced, okay? We've been talking about this forever, right? When you have atoms are rubbing against each other, that's what causes heat. Right? We talked about this. When you move your hands together, it gets warmer, right? And when you're outside and it's cold and you're moving your hands together, do you move them like this because that gets them nice and hot and toasty? No. What do? You do it really fast. And the faster you rub it, the hotter it gets. That's why when you start doing, if you're out stuck in the woods and you're lost and they say rub two sticks together and it'll eventually cause a fire, do you rub the two sticks together just like rub them like this? No. What do you have to do? You have to rub those sticks together really, really hard for a long time, right? The faster it goes, the more heat. And so the same thing with those molecules in the air. When the air is bouncing around, the faster it's going, the hotter it gets. That's kind of what happens in your microwave a little bit, all right? Think of it, your microwave getting hotter, right? What's happening? Microwave is sending microwaves into your food, and it's making all the little water molecules in your food bounce. And the more they bounce, the hotter it gets, okay? So when it comes to thermal energy, the faster that it's rubbed together, the more heat is produced. Now, here's the key. All right? This is the one thing you're going to have to kind of remember and think about. When you are cold, you get cold, right? And you put that blanket on. Here's the question. And you get warmed up, right? Does all that cold air that's out there, well, that's a bad example. Let me back up, sorry. You're hot, right? You jump in a swimming pool, and it's nice and cool, right? Here's the question for you. Why did you cool down? Did you cool down because all that cold water made your body hot or cold? Sorry. Or did all that hot body temperature go into the pool and cool the pool down? Or warm the pool up? Sorry, I completely messed that up. You're hot. You jump in the cold pool, right? I know I confused you. Let me start over. Hot, cold pool, right? You jump in. So let me ask the question. Does that cold water make you colder? Or does your hot body make the pool cooler? Hotter. Did it again. Your hot body make the water hotter. There you go. Which one do you think? What's happening there? Pool's cooling you down, right? Everybody thinks pool's cooling you down, right? No. You know what's actually happening? That hot temperature that's in your body is actually leaving to go and try to warm up that pool. Now, obviously, is that happening to the point where your pool all of a sudden gets as hot as you? No, because there's so much water and so cool liquid that you can't heat the whole pool up, okay? But it is warming up because the heat is leaving the hot body to go to the cooler. And that's the key for today. That is one of the things you have to realize is that heat will always warm up the cooler object. So if you have a cool object, the heat is going to leave the hot side and go and try to warm it up. It is not the other way around. The cool doesn't go in and say, we're going to cool you down. It's that heat energy is leaving because the heat energy thinks it can heat up everything. So if you put hot water and cold water in the same container, what's happening? The hot water is leaving the hot water and saying, we're already hot, let's go warm them up. And so they're leaving to go to that cool water to warm it up, okay? When does it stop warming up? Absolutely 100% correct. Whenever they get to the same temperature. So if I have 100 and this is like 30, when I put them together, it's going to go until they are the same. Does it always go straight to the middle? Like 100 and 0 go to 50? Not always, okay? Sometimes it goes from 100 and 0 and then we get to like 20. Now both of them are at 20. Well, the hot one got cooler and the cool one got hotter until they're even again, okay? It doesn't always mean it's going to be exactly right halfway in the middle, but the hot will always, always, always leave the cold, and you'll see how this works tomorrow. But the hot will always leave the cold. So the two things so far you should know is, what is heat? It's rubbing together of the atoms, and the faster we rub, the hotter it gets. Common sense, right? And the other thing is, hot always leaves to go to cold, okay? Your last little thing you need to know is what a conductor and an insulator is. Conductors, choo-choo train, woo, woo. They drive the train through, right? They drive the train, they go through the tunnels, they do all that kind of stuff. That's how you can kind of remember a conductor allows heat to go through it, okay? An insulator does not. I know those are big fancy 5th grade words, but these are big fancy 5th grade vocabulary words. Conductor allows heat to go through it. Insulator does not. Let me give you the example, okay? You have a pot, right? You put the pot of water on your stove. What part is allowing the heat to get into your pot? The bowl part of it, right? What part is not allowing the heat to travel through? The handle, right? You ever notice that the handle is different material than the pot. Why? Because the pot allows heat, the handle does not. What would happen if they were both made out of the same material? You burn your hand, right? You go to pick it up and that is hot too, because if they were both conductors, it would allow the heat to go through. So when it comes to a pot, we want part of it to let the heat go through, right? If not, your pot's not going to heat something up. But we also don't want all of it too hot, because then if you try to pick it up, you're going to burn your hand. And here's the key. Metal. Metal, metal, metal. Always think of this. Metal is the best conductor. Think about all your pots and pans. What are all your pots and pans made out of? Metal. What is all of the your stove, your pans that you put in the stove, all the racks that are in the stove, everything in the stove that gets hot, what is it made out of? Metal, right? But on the flip side, there are insulators. We don't want the heat to get through, right? On the outside of your stove, you have what they call insulation. I know you've probably never seen this, but if you took your stove and you busted open the panel of your door, guess what's in between the stove door, the front and the back? You have all this insulation. You've probably seen this in your house. This stuff. You ever go up in your attic and see all that stuff up in the attic? That's all that fluffy, fiberglassy, itchy stuff. You guys know what I'm talking about?
No.
Yes, no. Okay. You go up in your attic, go home tonight and ask mom or dad, say, hey, can I just look in the attic real quick? I just want to see the insulation. Why do we put insulation in our ceiling? Right, in the summertime, that insulation keeps that hot sun from coming through your roof into your house, right? And also, right, it also, when it's cold outside, it doesn't let the cold come through either, right? It keeps that heat inside our house. That's why all of your walls, all of your ceilings, everything is it's all insulated. It keeps the heat in when you want it hot, or it keeps the cool in when you want it cool. Depends on the time of year, all right? Insulation blocks the heat, okay? That's why all of your handles are made of like plastics or even ceramic. Some of them are foam. You guys have seen these kinds of foam, especially on all these poles as we're going to lunch. You guys seen the foam stuff all around it? You know where they just took off the ceiling of all the walkways, and there's all those pipes there. When we go today, look and see if you can find foam around some of those pipes to keep the insulation, keep the heat in, and keep the cold out. Your thermoses, a lot of you guys, you poured hot water in a thermos, right? Do you burn your hand? No, because if you look inside your thermos, there's insulation in between the inside layer and the outside layer. We're going to do a whole thing in a couple days about what the best insulators are and what the best conductors are, and we'll get into that. And we'll come back to this here shortly. But we talked about thermal heat, right? Heat is when the faster atoms move, the faster it gets, the hotter it gets. We also learned that heat goes from hot, goes to cold, not the other way around. We also learned what an insulator and a conductor is, okay? The next, so online people, copy your notes, pause it, copy. The next part is light energy. Now, there's not much on this light energy. When it comes to light energy, light, you need to know, travels in a straight line. Okay, it's waves. So when there's a ray coming from the sun, it's coming straight to the earth. It doesn't like bounce out to Jupiter and curves back around here and then goes this way. Okay, think of it like a flashlight. You turn on a flashlight. You don't turn on the flashlight and it bends like this and goes that way, does it? No, you can't turn on your flashlight and it goes through that door and into that other room and then out the other door, right? Because light goes in a straight line. If I were to have an example, I usually use a ball. Okay, it's a straight line. I drop it, it goes straight line and bounces right back up. Now, what if I bounce it at an angle? It still comes at a straight line, bounces, and then bounces off in a straight line. I don't throw the ball and it goes woo like this and then hits. Okay, it goes in a straight line, ricochets and goes off in a straight line. It's like shooting a gun. You don't shoot a bullet and the bullet turns, okay? But if you shoot a bullet, sometimes you'll hit something and ricochet and bounce the other way. Sometimes it doesn't. Sometimes it goes straight in to your target. Sometimes it hits and bounces off. Sometimes it'll hit, bounce straight right back at you. Okay? Those are not good. Light does the same thing. In fact, we're going to use some vocabulary words here that's really important. Light, since it travels in a straight line, one of the things that we're going to say is it reflects. Okay? Reflect means bounce back. You look at your reflection in the mirror. What's reflecting? The light of you actually seeing your picture. It's the light actually bouncing straight back to your eye, and you're seeing yourself as a reflection. Reflection means to bounce off. Okay? So when we're talking about light, using your ball, it bounces off, straight off, comes right back. That's a reflection. Another one, the opposite is, well, I'm going to come back to that one. The opposite is absorb. Absorb means it doesn't bounce off, it just stops there, okay? Sometimes you shine a light at a wall and it hits the wall. Does that light sometimes bounce off and hit you in the eyes?
No.
Sometimes. If you like shine it on a window or a mirror, you can see that light bouncing back to you, right? But sometimes you shine that light on a wall and it hits the wall and it stops there, right? It doesn't bounce off. It doesn't go anywhere else, okay? Sometimes it just stops there, and that's called absorbing. Absorbing is like a sponge, right? Sponge absorbs water. What's it doing? Sucking the water up, right? Sometimes light gets absorbed, and what is it doing? It's not actually bouncing off. It's actually just hitting that wall or hitting that object, and it's just kind of almost like it's being sucked in, and it's just staying there, okay? The last one, which is a little tricky, is actually refraction. Oh, that. Sorry. All right, so the refraction. This one is kind of weird because it does not bounce off. Sometimes you can bend light. You can, and what I mean, it's not like I can bend it and go all the way around everything. If I can just bend it slightly, sometimes light can bend. This is called a refraction. The way this happens most of the time is through a prism. All right, a prism is something like this. A prism is a little, like clear triangular piece of glass or plastic. And if I were to shine the light straight through one side, it's going to kind of bend. And in fact, it'll actually bend up or bend down in directions. Okay? I don't know if this is going to work because I don't have the right light, but we'll try it. For the online people, I'm sorry. You may not be able to see it, but we will try with a light. I don't know if this will work. Okay? Well, let me get away from that. All right, so it's not really bending very well. I'll have to get the other one. Maybe we'll do this tomorrow. But refraction is bending light. Now, every year I have people that they can't remember refraction, reflection. I don't remember which is which, okay? If you look at this, the only difference is the L and the R between the two. Refraction, reflection, R and L, right? If you look at an R, doesn't it kind of curve? And if you look at the L, isn't it kind of straight? So there you can kind of, that's the only thing, only little hint I can give you is refraction has a bend, reflection has the L because it's straight, refraction has the R, which is the bending letter, okay? Any questions on thermal or light? I know today was a long day, but here's your notes. I'll let you copy these, online people, real quick, pause it, copy it, copy this one. So again, there you go. Light energy, reflection, refraction, pause it, and absorption or absorbing means it stops there.